A magnitude 7.5 earthquake just struck Japan. 90,000 people were ripped from their homes in the middle of the night. Tsunami alerts screamed across every phone, every speaker, and every emergency broadcast system along the northeastern coast, the exact same coastline that was completely swallowed by the ocean back in 2011. Waves came. They hit. Evacuation centers filled. And the world held its breath, watching, waiting, praying this was not a repeat of the worst maritime disaster in modern history. But here's what the headlines are not telling you. Just beneath the floor of the Pacific Ocean, buried under miles of dark, crushing water, scientists recently made one of the most disturbing geological discoveries in decades. A record-breaking drilling expedition went deeper into the seafloor than any scientific mission in history, and what they pulled up from that fault zone changed everything we thought we knew about Japan's earthquake risk. They found a hidden layer, a naturally built weakness locked inside the geology itself, something that has been sitting there silently for millions of years, invisible, undetectable from the surface, and it may be the real reason the 2011 tsunami grew so monstrous, so fast, so unstoppable. Not just the earthquake, not just the magnitude, something else entirely. Something that was always there, waiting. And now that same fault zone just moved again. Today's 70-centimeter waves were serious enough to trigger mass evacuations across multiple prefectures. But the scientists watching the seismic data right now are not just measuring wave heights. They are asking a far more disturbing question. Did this earthquake interact with that same hidden layer? Did it slip along the same geological trap that turned 2011 into a catastrophe? And if the answer is yes, what does that mean for the next one? Because if this discovery tells us anything, it is this. The ground beneath Japan does not just shake. It has a preloaded path, a built-in weakness, and the Earth already knows exactly where to slip. So is Japan sitting on a geological time bomb. And did today's earthquake just start the clock? At 10:47 p.m. local time, the ground beneath the Pacific Ocean off the coast of Ishikawa Prefecture lurched violently. A magnitude 7.5 earthquake, one of the most powerful to strike Japan in years, tore through the seafloor with a force that seismic monitoring stations detected within seconds. The Japan Meteorological Agency issued its first tsunami warning at 10:51 p.m., just 4 minutes after the initial rupture. 4 minutes. That is all the time coastal communities had before the alerts hit every phone, every emergency speaker, and every broadcast channel along Japan's northeastern coast simultaneously. 90,000 people were ordered to evacuate immediately. Not suggested. Ordered. In the dark, in the cold, families grabbed emergency bags and ran. Elderly residents were carried from their homes by neighbors and emergency volunteers. Children woke to sirens they had heard before, or heard their parents describe with trembling voices, and they knew exactly what those sirens meant. The epicenter was located approximately 40 kilometers off the Noto Peninsula, at a depth that immediately alarmed seismologists monitoring the event in real time. Initial rupture data showed the earthquake had broken along a section of the fault system that sits within the broader Japan Trench subduction zone, the same geological region that produced the catastrophic 2011 Tohoku disaster. That detail did not go unnoticed. Within minutes of the first seismic readings, research centers from Tokyo to California were pulling up the data. Tsunami monitoring buoys recorded the first wave signatures at 11:03 p.m. By 11:19 p.m., wave heights of 70 centimeters were confirmed striking the northeastern coastline near Wajima. 70 centimeters does not sound catastrophic, but at tsunami speeds, across open coastline, a 70-centimeter wave carries enough force to knock a person off their feet, flood low-lying roads, and overwhelm unprepared communities in minutes. And every seismologist watching the data understood clearly that 70 centimeters was not necessarily the ceiling. It was the opening number. Japan's self-defense forces mobilized within the hour. Helicopter units deployed along the coast. Emergency operations centers in affected prefectures activated full crisis protocols. The Japan Coast Guard repositioned vessels for potential search and rescue operations. Evacuation shelters opened across Ishikawa, Toyama, and Niigata prefectures, filling rapidly as residents poured in from coastal neighborhoods. First responders on the ground described scenes of controlled panic, people moving fast, moving scared, but moving. Japan's decades of tsunami preparedness training were visible in every evacuation line, every shelter registration, every family that reached high ground before the waves arrived. But the physical waves were only part of what hit Japan that night. Beneath the seafloor, something far older and far more dangerous had just made itself known again. Japan sits at one of the most geologically violent intersections on the planet. The Pacific Plate, an enormous slab of oceanic crust moving at roughly 8 centimeters per year, is driving itself beneath the Eurasian Plate in a process called subduction. Think of it like two massive pieces of the Earth pushing against each other, one slowly grinding underneath the other, locking together under enormous pressure, and then suddenly, violently releasing. That release is an earthquake. And when that earthquake happens beneath the ocean floor, it does not just shake the ground, it moves the water above it. And moving the ocean is how you get a tsunami. The Japan Trench is the name scientists give to this specific subduction boundary, a deep underwater canyon that runs for roughly 800 kilometers along Japan's eastern coast. It descends to depths of nearly 8,000 meters in places. It is one of the most seismically active fault systems anywhere on Earth. And it is the same fault system that produced the most devastating natural disaster Japan has experienced in living memory. March 11th, 2011. The Tohoku earthquake struck with a magnitude 9.0, one of the 5 most powerful earthquakes ever recorded by modern instruments. The ground ruptured along a section of the Japan Trench approximately 500 kilometers long. The tsunami that followed reached heights of 40 meters in some locations, traveled up to 10 kilometers inland, killed nearly 20,000 people, and triggered the Fukushima Daiichi nuclear disaster, the worst nuclear incident since Chernobyl. The numbers from 2011 are staggering. But what confused scientists for years afterward was not the magnitude of the earthquake itself. A magnitude 9 event is capable of generating a devastating tsunami. What confused them was the scale of the seafloor displacement. The ocean floor had moved further, faster, and more dramatically than the seismic models predicted. The rupture had traveled shallower than expected, closer to the surface than a fault of this depth should have allowed. That mystery sat unanswered for years, until a drilling ship pointed itself at the exact spot where the rupture happened, and pulled the answer out of the seafloor itself. What scientists found buried down there would change the way the world thinks about tsunami risk forever. And tonight, that same seafloor just shook again. Scientists do not guess when lives are at stake. They go to the source. And in the years following the 2011 Tohoku disaster, an international team of researchers did exactly that. They sailed directly to the fault zone, positioned a drilling ship above the rupture site, and began pushing a drill into the ocean floor deeper than any scientific expedition had ever gone before. The ship was the Chikyu, a Japanese scientific drilling vessel purpose-built for deep-sea research. Its name means Earth in Japanese, and the mission it was carrying out lived up to that name entirely. The Chikyu is not a small research boat. It is a 210-meter drilling platform equipped with technology capable of penetrating the seafloor to depths that would have been considered impossible just decades ago. For this expedition, it was positioned above the Japan Trench subduction zone, directly above the section of the Pacific Plate that dives beneath Japan, right at the zone where the tectonic locking, the pressure buildup, and ultimately the catastrophic release of 2011 had all occurred. The drilling operation that followed broke records, not informally, officially. The Guinness World Records recognized this expedition for drilling deeper into the ocean floor than any scientific mission in history. The technical achievement alone was extraordinary. But what made it genuinely historic was not how deep they drilled. It was what they found when they got there. Core samples, physical pieces of the fault zone, pulled up from the earth in cylindrical sections, layer by layer, like pages being lifted from a book that had been buried for millions of years. Scientists who have spent careers studying geology understand that drill cores are not just rock, they are a record. Every layer represents a period of time, a set of conditions, a chapter in the story of how the Earth formed and moved and changed. These cores were pulled from the actual rupture zone of a magnitude 9 earthquake. They were, quite literally, pieces of the mechanism that killed nearly 20,000 people. And inside those cores, the team discovered something they had not anticipated. A distinct band of material running through the fault zone, a layer sitting approximately 100 meters thick, sandwiched between the harder surrounding rock. 328 feet of it. A layer as tall as a 30-story building, composed entirely of something called pelagic clay. Fine, soft, deep ocean sediment that had been accumulating on the seafloor particle by microscopic particle for millions of years, slowly building up like the quietest geological force imaginable. It looked unremarkable in photographs. Ancient mud, essentially. But what it meant for the physics of the fault zone was anything but ordinary. Ancient ocean mud sounds like the least threatening thing imaginable. It is not a supervolcano. It is not an unknown mega fault. It is not some dramatic hidden rupture waiting to be discovered. It is sediment. Microscopic particles that drifted down through miles of ocean water and settled gently on the sea floor over millions of years. Soft, fine-grained, completely unremarkable to look at. And yet this particular layer of clay is now considered one of the most significant geological discoveries in modern seismology, because of what it does when the Earth moves. Think of two rough concrete blocks being pressed together under enormous weight. If you try to slide them against each other, the friction is immense. The rough surfaces catch and grind. They resist. Now imagine you spread a layer of soft grease between them, something smooth, something slippery, something with almost no internal resistance. Suddenly, those same two blocks slide against each other easily. The friction is gone. The resistance disappears. They move fast and they move far. That clay layer is the grease. During the 2011 earthquake, tectonic forces that had been building for decades along the Japan Trench concentrated directly along this band of pelagic clay. Instead of the rupture having to tear through hard, resistant rock, which would have slowed the movement and limited the displacement, it found this smooth, weak pathway. The rupture did not grind. It slipped. It accelerated along the clay layer and kept moving, all the way from its deep origin point toward the surface, reaching the ocean floor itself. That is the critical detail. The rupture reaching the ocean floor. When a deep earthquake ruptures but does not reach the seafloor, the shaking is transmitted upward through rock and water. Destructive, yes. Capable of generating some tsunami activity sometimes, but not like this. When the rupture reaches the seafloor and the ocean floor itself physically moves, the entire water column above it is displaced. Not shaken, displaced, physically lifted. In the case of the 2011 earthquake, the ocean floor was raised by an estimated 40 to 60 meters across a vast area in seconds. Imagine lifting the bottom of a bathtub 50 meters while the water is still in it. The water has nowhere to go but outward. That is your tsunami, not a wave generated by shaking, but a wall of water generated by the physical displacement of the ocean itself. That is what hit the northeastern coast of Japan in 2011. That is why the waves were so tall, so fast, and so catastrophically far-reaching. The 2011 tsunami was not a freak of nature. It was a geological consequence, one that the Earth had been quietly preparing for millions of years. The 2011 discovery changed the way scientists model tsunami risk along the Japan Trench. But a discovery only matters if it can be applied, if it changes how we prepare, how we calculate, how we anticipate what the Earth might do next. And then, before the full implications of that research had even been mapped across the fault system, the ground moved again tonight. A magnitude 7.5 earthquake rupturing along the same fault system that produced the 2011 event is not a minor footnote. It is a data point that every seismologist monitoring the Japan Trench is now analyzing with the clay layer discovery at the front of their minds. The immediate question is not only how big were the waves. The immediate question is where exactly did this rupture occur? How deep was it? And did it interact with the same geological weakness that turned a large earthquake into a civilization-altering disaster 13 years ago? Preliminary seismic data from tonight's event is already being scrutinized for signs of shallow fault behavior. Rupture depth is one of the most critical variables. A rupture that initiates deep and stays deep behaves very differently from one that propagates toward the surface. The 2011 earthquake surprised scientists with how shallow its rupture ultimately traveled. If tonight's event shows similar characteristics, if the rupture depth analysis reveals movement along the upper portion of the fault, that is information that cannot be ignored. The 70-centimeter waves recorded along the northeastern coast are being treated as more than a tsunami measurement. They are being treated as a geological signal. Wave height is not just a number. It is the surface expression of everything that happened beneath the ocean floor. The depth of the rupture, the amount of seafloor displacement, the presence or absence of that clay layer acting as a slip pathway. Scientists are reverse engineering the wave data to understand what the fault actually did tonight. But the scientific community is now grappling with something the evacuation drills cannot fully address. If the clay layer extends further along the Japan Trench than currently mapped, if tonight's rupture touched even a portion of that weak geological pathway, then the risk calculation for this fault system needs to be revised upward again. And if it needs to be revised for Japan, the next question is unavoidable. Where else does that revision need to happen? The waves from tonight's earthquake have receded. The tsunami alerts have been downgraded. The 90,000 people who fled their homes in the dark are slowly, cautiously beginning to return. The seawalls held. The warning systems worked. The evacuation routes did their job. By every measure of disaster preparedness, Japan's response to tonight's magnitude 7.5 earthquake was a demonstration of how far this country has come since the horror of 2011. Lives were protected. The infrastructure performed. The drills paid off. But the geology has not changed. Beneath the floor of the Pacific Ocean, in the darkness where no human being will ever stand, that layer of pelagic clay is still there. 328 feet of ancient, soft, slippery sediment, sitting silently inside the fault zone, sandwiched between harder rock, waiting. It waited for millions of years before 2011. It is waiting now. And the most important thing the record-breaking Chikyu drilling expedition gave the world was not just an explanation for what happened 13 years ago. It was a warning about what the geology of this fault system is fundamentally capable of doing again. The clay layer discovery has already begun reshaping how scientists calculate tsunami risk, not just for Japan, but for every coastline that sits at the edge of a subduction zone along the Pacific Ring of Fire. Cascadia, Chile, Indonesia, Alaska. Every one of those fault systems is now being examined with a new and urgent question. Is the same weakness present? Is there a preloaded slip pathway buried in the seafloor, invisible from the surface, undetectable without drilling, waiting for the right amount of tectonic pressure to find it? We do not yet have all the answers. The mapping is incomplete. The science is still catching up to the implications of what one drilling ship pulled out of the ocean floor. What we do know is this. The Earth beneath Japan moved tonight. It has moved before. It will move again. And somewhere beneath the Pacific Ocean, in a layer of mud so ancient it predates human civilization by millions of years, the path is already there.